It sure is hot today. I'm glad we have this pool to help cool us down.
Speaking of which, have you noticed that when your feet are in the pool, your legs are larger than they normally are?
Huh? You're right. I finally hit my growth spurt.
Calm down, would you? Your legs don't feel any longer than normal, right?
I guess not. But that's just how tall people are.
No, it's because you aren't actually any taller.
What? My feet look bigger, so wouldn't that mean I'm taller?
Nope, it's all because of something called optics.
What is that?
Optics is derived from the Greek word meaning appearance or looks, but in this case, it refers to the study of light.
How does light have anything to do with me having a growth spurt?
Well, it doesn't. That's genetics. But the reason you look larger in the pool is due to the behavior of light. Light is unique in nature as it behaves as both a wave and a particle. It acts as a wave because it oscillates, meaning it moves between two different points in a specific and steady pattern. Variation in these waves are responsible for how we see and perceive color, but that's getting off topic. Light acts as a particle as well, traveling in rays, which leads to the reason your legs look larger. In a vacuum, light travels in a straight line at 3.00 times 10 to the 8 meters per second, which is the fastest speed in the universe and is represented in physics with the letter c. Now, it might be worth noting that this is in a vacuum, which of course isn't frequently experienced in nature on Earth. Air does slow light down a little, due to the different particles that it can hit and be bounced around by. The bouncing around and slowing of light through a material is referred to as refraction. Refraction varies with each material the light must pass through. In fact, there is a mathematical relationship that describes this. N, which is the refractive index, measure of the light bending ability of a material, is equal to c, the speed of light in a vacuum, divided by v, the speed of light in the given material. One refractive index that is commonly encountered by people is that of air, which is 1.0003, meaning light in air is only slowed down by 0.0003 times compared to when it is in a vacuum. In most cases, this makes the refractive index of air approximately 1. Additionally, the refractive indices of water, 1.33, glass, 1.46, and plastic, 1.49, are commonly encountered. These refractive indices change the angle at which the light travels between two media. In the pool example, the water has a larger refractive index than air. This means that when a light ray hits the water, it bends closer to the normal, which is perpendicular to the media, forming a smaller angle. Our brain doesn't account for this smaller angle and behaves as though the light hasn't bent, which makes us think that the object is larger than it actually is, which can also make us think things underwater are closer, such as the bottom of a pool looking shallower than it really is when you jump in. This relationship between refractive index and angles is described by Snell's law. Snell's law states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant when it passes between two given materials. In this video, you can clearly see the difference in how light travels between two media. At first, the light is only traveling through air, which, as a reminder, has a refractive index of 1.0003. When the flashlight is held in the same location over water, which has a refraction index of 1.33, the beam of light doesn't land in the same spot as before. Instead, it is closer to the glass because of the smaller angle of refraction. In addition to understanding why things look the way they do, knowing how refraction affects light is relevant for practical uses. High magnification microscopes use oil between the lens and slide because of its higher refractive index, 1.51, because it makes the subject appear closer. The refractive index of glass is how microscopes and magnifying glasses work to begin with. Glasses also use refraction to correct vision, and even our eyes refract light. So yeah, that's why your legs look large in the pool, because of light refraction from differences of light's ability to travel through water and air.
Wow, that's a lot more complicated than I expected. I was really hoping it was because I was getting taller.
Yep. Physics makes everything complicated.
I just have one question.
What is it?
What are we vacuuming, and why do the snails have laws?
I'm going to find a different pool. My knowledge is unappreciated here.
Wait, get back here!